and then we'll be done if we. I mean, if not, we can take 15 minutes tomorrow, but I don't know who else is doing what today. We'll give Caitlin a second. Yeah, it's
Sorry. If I didn't do the last assignment for chemistry, would I still get my credit?
I don't know. I think you should because it's probably the most important one. Um, but or do some of it, or
I'm gonna do it. I was just gonna see.
I mean, I won't say no, but the more you do, the more you'll be prepared. And if you've done everything else, I mean, it's just going to be a check or an X, I guess. I don't know. I got an email about grade 9 and 10 report cards last week and ignored it because I don't have any grade 9 or 10s. But if Caitlin shows up, well, the last thing quickly to go through is gases. There's like 3 pages. Apparently there was 9 pages that got posted. Um, we'll go through this. There won't be any questions anywhere or any assignments. The last one that's up there is what we have. I don't know where my head ends up looking if I lean back in the chair because it's a whole different ball game here. Oh, there's Caitlin. Morning. Um, General properties of gases. Where's my cursor? What's going on? There we go. Gases are different than solids and liquids because um, they have no shape or volume. A liquid has a definite volume but no shape because you can change the shape of a liquid, and solids have a definite or defined shape and volume. Um, Gases are different. Gases you can compress. You can compress a solid with really high pressures, but it's not common. You can kind of compress liquids a little bit, but gases, you can take a gas and compress it drastically because of how particles move. Gases are mainly empty spaces. Um, Gases can diffuse and mix. This diffusing thing, if you think of an odor, if when Dunster started baking this morning, because that was the smell I got when I opened my car. When they started, that odor would have been at the building. By the time I got here, it was all the way over to here, if not further. They mix, air is a mixture. Whoops, I guess I need a. Densities are relatively low. A balloon, for the most part, is fairly light. Gases consist of large particles moving in continuous, rapid, random motion. And so the air, there's all sorts of things. Collisions of gas molecules uh, with the walls of a container are elastic. They bounce back. They just kind of volume occupied a gas molecule themselves is negligible because they're relatively small compared to the size of the container. Too far apart for attractive forces. Um, this is one of the things why is, I mean, most gases tend to be atoms like argon, neon, even diatomic molecules are very nonpolar. Most gases tend to be nonpolar. Temperature, we need Kelvin units, which is really easy. We'll talk about that in a second. Um, is a way to measure the kinetic temperature is a measure of kinetic energy. So if you have a high temperature, you have lots of kinetic energy. At a low temperature, molecules move slower, decreasing their average kinetic energy. Gases fill containers quickly, they diffuse rapidly, they're easily compressed, low density, and it's all random motion. So pressure is kind of the key thing. That's what you talk about. You go to, if you wanted to buy a cylinder of some sort of gas, you get a pressure reading. Pressure is affected by the amount of gas, moles, Increasing the number of things increases collisions, which makes more pressure. Volume, think of a balloon. Increasing the volume will decrease the pressure and vice versa. We'll talk about that in a minute. And temperature increases the speed, which leads to more collisions. So those are the three things: amount, volume, and temperature. And units of pressure are they're all over the place. There's one that we use a lot called atmospheres, which is technically metric, but it's kind of a standard one. Atmospheric pressure is like set to one, and everything goes based on that. Kilopascals is metric. These two are equivalent. Metric or torcelli, it's named after a scientist, and millimeters of mercury have to do with how they used to measure pressure with an actual thing of mercury. I think there's one down in Mrs. Parley's room. Pounds per square inch. This is where what you talk about in your tires. You have 33 pounds per square inch or whatever. An atmosphere of pressure is 101.325 kilopascals. This is the metric one. Pascal is a scientist, so this is 1,000 pascals. And a pascal, I think, is a kilogram per meter squared. So if you think of like a classroom, the tiles are roughly a square foot, so 9 of them ish is about a square meter. So a pascal of pressure would be if you took a kilogram and spread it out over that whole square meter. 101 kilopascals will raise mercury 760 millimeters, or that's equivalent to 14.7 psi. So my tires are somewhere between 30 and 35. So my car tires are actually twice what average atmospheric pressure. Um, we can convert based on kind of any of these. If I took 0.89 atmospheres and wanted it in torr, 760 is 1 atmosphere. So 0.89 atmospheres is 760 torr. Um, the weather network normally um, will relate atmospheric pressure. Uh, and we can tell a high pressure system is nice and warm. A low pressure system is generally rainy and all of that. Hurricanes have the lowest pressure. Come on. Oh, there we go. Yeah, whatever. Go away. Well, I can scroll up so we can see it. So pressure right now in Sussex, according to the Weather Network, is 100.7 kilopascals, which is slightly below average atmospheric pressure, um, but that changes because of the weather. So there's three laws in terms of gases before we get to what we call the ideal gas law. Boyle was a British guy. If we keep temperature constant, the pressure of the gas increases as the volume decreases. So pressure times volume is a constant. So this idea is um, if you take a balloon and you squeeze on it, you're decreasing the volume. You can feel it a little bit more. It pushes out more because you've decreased the volume and increased the pressure. So the kind of things that we would do, P1, pressure 1 times volume 1 is pressure 1 times volume 2. A balloon contains 30 liters of helium at 103 kilopascals. What volume would the balloon be if it was 25 kPa? So P1, V1. And you can use the ideal gas law to do some of this. So pressure 1, 103. Volume 1 is 30 liters equals 25 So we're going to divide both sides by 25. I'm trying to be quick. I'm getting sloppy. Divide by 25. So this is going to, the volume is going to roughly quadruple. 103 times 30 divided by 25. So if you decrease the pressure that significantly, the volume would increase from 30 liters to 123. Normally, people think about this in terms of in changing the volume. Actually, they used to. Lord knows where it is now. Have an old-fashioned syringe. It's probably sitting in a box somewhere. If you take a syringe and pull it all the way out and plug it, if you decrease the volume, eventually you get to a point where you can't compress it anymore. You've increased the pressure. And if you take your hand off of it, the stopper pops back up to relieve that pressure. So we've got Boyle is an English guy. Apparently in 1662 came up with Boyle's law relating that. Charles was French in the 1700s. If the pressure is constant, the temperature, um, as the temperature increases, the volume increases. As the temperature decreases, the volume decreases. Most people have seen this in the winter in their car. If you take a bottle of water, an empty water bottle or pop bottle or whatever, and you have it in your car and you're driving and it's warm enough that you're okay, and you stop your car and you go in your house and it goes down to 20 some odd below zero that night. Well, there's a 40-ish degree difference in the temperature. What happens to that bottle when you get in the car in the morning? It sucks in. So this is an inverse kind of relationship. The ratio of volume to temperature is a constant, so we use V1 over T1 equals V2 over T2, V1, T1, V2, T2. A balloon is inflated at 24 degrees Celsius. We add 273 to get Kelvin temperature, 297 Kelvin. We need to do this because degrees Celsius is a great scale. 1 degree Celsius is 1 degree Kelvin. Celsius temperature is predicated on water. It freezes at 0. It boils at 100. But the problem mathematically is 0 degrees Celsius causes some trouble. So after people figured that out, they went to what they call an absolute temperature scale. The lowest physically possible temperature to get is negative 273.15 degrees Celsius. You cannot get colder than that. It's not physically possible because of quantum mechanics and all sorts of things like that. So if we set this to 0 and then everything else goes up, we get this nice nifty scale. So 24 degrees Celsius is 297 Kelvin. 0 degrees Celsius is 273. And we don't have this problem with dividing by 0. 4 liters. It's heated to a temperature of 58 degrees Celsius plus 273 is 8 and 3 are 11. 7 and 1 are 8. So that's 341 Kelvin, and we want to know that. Move the temperature, V1 times T2 over T1 equals V2. You can think, oh, well, because it's a ratio of those temperatures, you can just leave it in Celsius. But quickly with the calculator, 58 divided by 24 is 2.4. 341 divided by 297 is 1.14. You get a very different answer. So 4 liters times 341 Kelvin, well, you heat it up. You should increase the volume. If you put a balloon, a small balloon in a stove, it will expand. Um, Not that anyone should ever do it. If you put an aerosol can in a fire, that's why they blow up, because you increase the temperature so much that the gas inside expands, and that would be very bad. So don't ever do that. It's very dangerous. 4 times 341 divided by 2, 297 is, so your new volume, 4.59 liters, which in this case isn't a drastic increase, but a fire is a couple hundred degrees Celsius, so it's going to increase it by that much more. So Boyle, Charles, and then another French guy whose last name was Gay-Lussac, um, looked at pressure and temperature, and it's a similar idea because pressure and volume relate. Pressure over temperature. If you increase the pressure or you increase the temperature, you increase the pressure. Hey, the gas in an aerosol can is 103 kilopascals at a temperature of, that's 298 Kelvin. Is thrown in a fire. The temperature is 928. 8, 11, 10, 1200 Kelvin. What is the final pressure? And then what happens after that? I would P1 or T1. Pressure 2 is P1 T2 over T1. Just to switch it, 103 kPa times 1200 Kelvin divided by 298 Kelvin. Oops. Arg, sorry. 1003 times, you now have a pressure of 415 kilopascals, which, oh, just to put that in terms of perspective, uh, is that many atmospheres, which would be the equivalent of filling a tire to about 60 pounds per square inch, which, depending on how the can is and all of that, it's not all that great. We can do what's called a combined gas law, where we have pressure, volume, and temperature, and pressure times volume equals pressure times volume, but we have that reciprocal relationship. This one is, um, here's, instead of 3, find the fourth, but normally you can find a pressure, you can find a temperature, you can find a volume. The volume of a gas filled balloon, 30 liters, at a temperature of, and a pressure of, what would be the volume at standard temperature and pressure? Volume equals question mark. Temperature 2 at standard temperature is 0 degrees, degrees Celsius. 0 degrees Celsius plus 273 Kelvin equals 273 Kelvin. Standard temperature and pressure. Pressure is atmospheric. We have enough information. P1 V1 over T1 equals P2 V2 over T2. T2 goes up, P2 goes down, so pressure 1, volume 1, temperature 1 over temperature 1, pressure 2 equals volume 2. This is where I would probably use a fancier calculator, but oh, I'm going to put numbers in. Uh, pressure 1, volume 1, 30 liters. Temperature, oh, that should be temperature 2 divided by temperature 1. Let's make sure we can read this. 300 Kelvin times pressure 2 kilopascals, kilopascals, Kelvin, Kelvin. We're left with volume. Bracket 153 times 30 times 273 bracket. What? That's, well, let's see. That's not open bracket. 53 times 30 times 273 close bracket divided by open bracket. This is where you're using the brackets on your calculator. Point to it with your finger, dummy. They can't see that. The three numbers in the numerator multiplied divided by the product of those equals volume 2 is 39.5 liters. Pressure has gone down. Temperature has gone down. It makes sense that that goes up. No. So where we kind of combine these, which is something called the ideal gas law, which works at most normal conditions. If you have really low pressures, temperatures, or really high pressures and temperatures, which are not really dealt with by anybody on a daily basis, this doesn't really hold true, and there's corrections in all of this. Um, but if you don't mind, I think we'll stop here and we can do that, finish that tomorrow, and look at a couple of questions, and that'll be everything, unless you guys want to power through and do a couple of these today. Do you want to come back tomorrow or keep going?
Doesn't matter to me. Yeah, we got there.
All right, let's finish.
You pick.
All right. Well, if we go through these three examples, we'll be kind of done, and we don't really have to keep going unless we want to go back and revisit the empirical formula was something that I wanted to go through, and this the ideal gas law is something that can come up. Um, if you have a sample of something, we can vary pressure, we can vary temperature. We talked about in moles at standard temperature and pressure, 1 mole of gas has a volume of 22.4. So this kind of relates that, so you can determine any one of those four amounts if you have three of them. But we have this other thing, it's called the ideal gas constant. Um, it really fundamentally depends on pressure units, but it relates, it kind of fits all of the numbers together. So it's a great big, can be a great big mess, an array, but if you're given pressure, volume, and temperature, you can actually figure out how many moles of a gas there are. So kind of one of my favorite questions at the end of an exam is to give it used to be a limiting reagent problem where you have a concentration and a volume of one thing, you have a mass of another, you produce a gas, and I ask you for the pressure because stoichiometry is based on moles. If you have moles and I give you volume and temperature, you can find the other one. So R, if it's in atmospheres, is 0.08206. If it's in kilopascals, it's 8.314. And I think both of those are on your periodic table if you ever forget them. So a deep underground cavern contains volume equals 2.24 times 10 to the 6 liters. Volume has to be liters. Temperature is in Kelvin. Pressure is in pressure. Moles are in moles. Volume is this. The pressure is 1.5 times 10 to the 3 kilopascals. The temperature is 42 degrees Celsius plus 273 is 315. R, because it's in kilopascals, is 8.314 liter kPa. You got to write units. PV equals nRT. I want moles, so I'm going to divide the other side. Pressure times volume over R times T. You have 4 of them. You're going to get 3 quantities, and then you get the fourth for free. So 1.5 times 10 cubed kilopascals. Well, PV over T, that's part of that combined gas law. And then we just tack R in there to give us moles. Pressure times volume, 2.24 times 10 to the 6 liters. A very big pressure, a very big volume. 8.314 liters kPa per mole Kelvin. Notice kilopascals and kilopascals are in the numerator. They cancel. And our temperature was 315 Kelvin. Kelvin cancels 1 over 1 over moles. So our units at the end are moles. Again, this is where our brackets come in handy. 1.5 exp3 times 2.24 exp6 bracket divided bracket 8.314 times 315 bracket. That number, if you're using this calculator, that's the product of those two. This doesn't, the exp button is very different from the 10 to the x from math, but we'll push equals. We get, holy smokes, 1.288 times 10 to the 6th moles, which is a massive amount of moles. An underground cavern contains a giant volume of methane gas. Could we convert that to a mass of methane and think about that, how much gas there is? Sure, but we have a ridiculous number of moles. Apparently,
Mrs. Smith, the answer to your question is it's not out yet.
the cylinder of argon gas contains volume, liters. Pressure is 18.4 atmospheres. Pressure is in atmospheres, so 0.06 liter mole Kelvin, and the temperature is 127 degrees Celsius. That's 10, 7, I think that's 400 Kelvin. This one is boring. We want to find moles. But we have more reasonable numbers. 18 atmospheres, 50 liters. Our gas constant is 0.08206 liter atmospheres per mole Kelvin, and our temperature is 400 Kelvin. 18.4 times 0.4 times 50 gives me that, divided by an alternative is to divide and then use your brackets. So this gives us a 28 moles times, I can't see, 39 or so grams per mole. Oh my gosh, we've got something different. What is the pressure? Volume is 5 liters. Moles is 0.0 moles. The temperature is equals 353 Kelvin. Pressure equals, I don't know. R equals, this is a question where if I gave it to you on a test, I would have to do it twice. I'm going to do it with this one. Liter, kilopascals. Because you could use 0.08206 and give me an answer in atmospheres. Both are equally correct. PV equals nRT. Divide by volume. Pressure equals moles times R times T divided by the volume. So 0.0350 moles. R, I'm going to run out of space. Per mole Kelvin times 353 Kelvin. Divide that by a volume of 5 liters. This one is a little bit easier with the calculator. 0.0350 times 8.314 times 353 equals, divided by 5. So these conditions would give us a pressure of 2. It's actually ridiculously small, but that's a small amount of moles. Any ideal gas law question, which if you look at the next page, you can look at. I don't know if the answers are at the very bottom or not. Moles, temperature, pressure. What's the volume? Temperature, pressure, volume, mass. Find moles. Temperature, oh, negative, convert to Kelvin. Mass, moles, volume, what is the pressure? I would convert that to, well, whichever one you want, atmospheres. That's the same as a liter. Fine, like the complicated things is, oh, calculate, convert grams to moles, which you guys are all capable of. But that is the gist of gases, the things that you would need to be able to do going forward. And that's about all that we absolutely need in Chemistry 11. So if you've gone through and looked at everything, you should be fine in Chemistry 12. We did get an email last week, the week before, I don't know, it all runs together about how curricula next year is going to be modified, changed, prioritized. There's a better way because modify has an old connotation. Um, to take into account that, well, a lot of you haven't done as much stuff. I hope the 3 of you have all signed up for Chemistry 12. And there's a whole bunch of other people who could. Oh, shoot. I apparently have to make a phone call or send an email later today. My wife's texting me. But that's all I have. So if you're planning on doing that last assignment, you have technically until Wednesday. But other than that, that's kind of what we've got.
In this class, how do we know if we get the credit or not? Or will we like be let? Will we know from like all of our classes?
There will be a report card, and I assume it's just going to have like chemistry 11 CR or ENR. Those are the two things. Um, but like you'll all of your numbers from first semester will be there, and then second semester you'll have that the CR and enrolled kind of thing. And I assume all three of you are gonna for this at least and math, or well, Caitlin didn't take math, I don't think, with me. But the three of you for sure will get your credit because I'm pretty sure all of your stuff is there, whether it was late or not. I don't particularly care, but so I don't know how they're going to get them out to you, but there is going to be a report card, at least to my understanding. So you'll have that. I don't know if it'll go in Power School. I wish I had more information, but thanks for keeping up with everything. Um, it's been odd and weird and different, but we've all endured. Next year will be hopefully a lot easier.
So, are we done like class now? We won't have any more classes tomorrow, and then the next day.
Yeah, that's all I have to go through unless you guys have questions and want to go over some stuff.
I
Just
had some questions on the assignment.
specifically what? Which questions?
For question 2, I wasn't sure if there's some information missing or if I was just doing it wrong, like using the wrong method, I guess.
Question 2. Oh, student view. Oh, at least this one I didn't have. That's question 1. Is just moles. Question 2. You have a volume and a concentration. That's a C equals N over V. You have to convert that to liters. Moles is concentration times volume.
Yeah, I guess I figured that out.
Uh,
Never mind, thank
oh,
you.
okay.
What about for number 6? Do we like balance that first and then like where do we go after from that?
So you would balance it, which really you need a 2 here. You have a volume and a concentration of potassium hydroxide. So if you have that, you can find moles. Then you need to find moles of sulfuric acid. If you have moles of sulfuric acid and a volume, you can calculate a concentration. So it's one of those 3-step. Find moles of one, convert moles to moles, and then find the concentration of the third. And that one, oh, that one's balanced. But 6 to 11. Does that help?
Yeah, it does, thank you. Is number 11 just kind of similar to 6?
Yeah, it's just you have a mass. You have to find your uh, moles of this using just the mass of that. So it's just an old-fashioned mass to moles conversion. It's just kind of adding a step.
Okay.
Well,
Thank you.
you can find the molar mass of sodium bicarbonate. So 23, 24, 36 plus 48, whatever that adds up to. Okay. And you can email me questions if you have other ones, if you need to.
Sounds good.
Awesome.
Alrighty.
Thanks for coming all the time.
Yep.
Ha,
Thank you.
we'll talk to you later. Have a good day.